Hello, and welcome to your final section of Chapter 5. I know you're probably ready to be done with this chapter. It has been a bit of an overwhelming ride, but hopefully this section won't seem as overwhelming. I don't feel like this information is as tough as the other concepts. This is more just, I'm not going to say common sense, but it's more of just like, I think it's a lot more logical, I guess is what I'm trying to say. But we'll take this baby step each baby step at a time, like we've been doing with the previous two sections. I did not include an objective slide, so I am really, really sorry. But we will go over what you should know at the end of this slide when we talk about it in class. All right, so we have been focusing on the atom and what the atom actually looks like. And then we started talking about the idea of the quantum mechanical model of the atom. And that is the modern and accepted model of the atom. So those quantum numbers, that is what is true to this day at this current moment. That is true to what the atom looks like, or how the atom is represented. So there are a couple things that I want you to know. Electron configuration is a new word, so you should highlight that word. What I'm talking about, what I mean by electron configuration, it describes the arrangement of all electrons in a particular atom. So remember, so many electrons make up a particular atom, and that atom, a combination of atoms, make up elements. And so we generally use the word element and atom very interchangeably. So again, remember, we don't know the exact location of electrons. Each electron exists in a particular space in orbitals, but again, we don't know specifically where. But we have an idea of where that is thanks to our quantum numbers. Remember our 4 quantum numbers. So we're going to use those ideas, and in class, I will go over a periodic table and label the periodic table on where those orbitals are located in regards to the periodic table. Now we have this idea of how to write these orbitals and how they relate to elements. So writing an electron configuration of an atom essentially lists which orbitals contain those electrons and how many electrons are in each type of orbital. So there's a pattern to this that we are going to practice in class. I promise you it becomes very repetitive, and this is why I'm telling you that once you practice it so much, it becomes pretty basic and just very repetitive. So electron configuration describes the arrangement of all electrons in that atom. Like I already said, each element has its own unique configuration. So you will never repeat your configuration. So if you have one configuration for an element, you should never use that again for another. All systems want to be in the lowest possible energy state. This includes electrons. So everything wants to be in the ground state. So we are going to talk about electrons that are not active. Remember, when they are active or excited, they're either losing or gaining a photon. So before we start talking about how to write the electron configuration for various types of elements, we need to understand a few basic rules in regards to the quantum mechanical model. So the 4 basic rules we're going to talk about, the first one is known as Aufbau's principle. And so what this states, in order to determine ground state electron configuration, which is just basically the electron configuration, it's necessary to organize the atomic sublevels in order of increasing energy. And so what I mean by that is that each orbital has a specific energy, and depending on the complexity of the atom, meaning how many electrons it has, will determine more energy. So if we're comparing hydrogen to an atom like sulfur, the energies are going to be so much different because of the fact that there are more subatomic particles found in sulfur than there are in hydrogen. And so lowest energy level is always the 1s sublevel. 1 meaning the lowest energy level, and then S would indicate that spherical shape. Those are your lowest energy. And so here, on this point here, I've listed the sublevels in order. I don't expect you to memorize this. I do have a chart on the next slide that you will copy. Hopefully you will copy down into your notebook. But you should know that as we progress through the elements, the energy levels increase, and so they're going to have a longer electron configuration. So Aufbau's principle states that all lower energy orbitals must be filled before electrons can be added to a higher energy orbital. And I know you probably can't visualize this now because I'm just listing these numbers and letters. So 1s, 2s, 2p, 3s, 3p, 3s, 4p, 3d, 5s, 5p, 4d, 6s, 6p, 5d, 4f. So I'm going to give you a visual on how this looks, and hopefully that will make a little bit more sense, because listing them like that I don't feel like gives you enough information. So like I mentioned in the last slide, Aufbau's principle states that all lower energy levels must be filled first before you can progress to the next energy level. So a few things that you're probably going to want to write down right now is that your energy level order or sequence goes S, P, D, and F. Your S orbital indicates your lowest orbital level, and they also hold the least amount of electrons. Again, we are going to go over this in class, and I will cover how many electrons each orbital holds, and then the total, how that coincides with our principal quantum number. But this is how Aufbau kind of described how things should be filled. Your 1s orbital is always going to be filled first. And so if we progress down, if we look going towards downwards, all of these have a different orbital. And so how they wrote this, or not different orbital, different energy, how they wrote this is they started with 1s at the top, 2s, and 2p, because they're indicating same energy level, same principal quantum number, just a different orbital within that principal quantum number. And then we have 4s, 4p, 5s, and so on and so forth. So I just wanted to make sure that you understood the way they got this was based off of those principal quantum numbers. Now, one thing you may notice about this is that and this makes sense. We got 1s, 2s, 2p, because the order is for orbitals, s, p, d, and f. So those make sense. Over here we have 1s, then you go down, you're going towards your 2s, and then you're going into your 2p, 3s. Makes sense, right? Because your second principal energy level can only hold orbitals s and p. We then go into, after 3s follows 3p and 4s. And this is where things kind of look a little funky, because if you remember your principal quantum numbers, principal quantum number 3 holds 3 orbitals, s, p, and d. So you would think that it would be 3s, 3p, and then 3d. Well, in reality, energy level 4s has less energy, just a little bit less energy than energy level 3d. So we fill 3p, oops, I didn't mean to move that, sorry. We fill 3p and then 4s, and then we continue on and we go 3d, 4p, 5s. If you follow this order that's given here and you follow the arrows as they progress down, you will do great and fine with electron configuration. Again, we will practice this together, so don't freak out right now. Remember, we're taking things very slow. You will be just fine. But the big thing I want you to take away right now is that the order goes S, P, D, and F. 1s indicating the smallest or lowest energy level. And on this diagonal rule or filling order, 7p would be the greatest. The next rule that we need to follow when we write electron configuration is known as Pauli exclusion principle. And what this is talking about is, one thing I want you to remember is that every orbital, no matter which type, is capable of containing 2 electrons. Every single orbital has the ability to contain 2 electrons. And the electrons in any completely filled orbital have opposite spins. That's why we have that spin quantum number that tells me whether I have a positive or negative spin, a positive 1/2 or negative 1/2. So again, every orbital can hold has the ability to contain 2 electrons. We go off of the orbital with the capability of holding the lowest electrons because every single orbital can hold those 2. So basically, this is summed up. What I just said is all summed up in Pauli's exclusion principle, in that no two electrons in an atom can have the same set of 4 quantum numbers, and that those electrons have different spins. I'm going to show you what this looks like in class, and so I'll explain. What you'll see is that generally this is written with boxes, and that you indicate the opposite spins by arrows. And I have this on the next slide as well, so I will explain them in further detail on the next slide on how you do the filling order. But remember Pauli's exclusion principle. No two electrons in an atom can have the same set of 4 quantum numbers, which you already know that, right? If I have a ticket to a basketball game, I am the only one that has that ticket to that basketball game. Meaning, even if they're just different by the spin number, that still makes them 2 different atoms, or electrons, excuse me. Third rule, we are now talking about Hunds Rule. And Hunds Rule states that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. And all electrons in singly occupied orbitals must have, I cut off my notes, hold on. The same spin is what I was trying to say. So, Hunds Rule again, orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron, and all electrons in singly occupied orbitals must have the same spin. And so I'm going to break this down looking at these 2 pictures that I have here. Oops, I didn't mean to do that. Erase that really quick. So what I'm going to explain to you is how we use Hunds Rule. So this is a way to keep electrons in order and not necessarily always have them paired. So how you figure this out is basically you determine how many electrons a particular atom has, a particular neutral atom has. So if I'm looking at boron has 5 electrons. So we are going to use those 5 electrons to place in my Hunds Rule, or my Hunds Rule diagram, also known as an orbital filling diagram. And so one thing I want to write down and have you write down right now is, remember I talked about previously the orbitals S, P, D, and F. Those are the shapes of each orbital. But we are going to give more information in regards to those. So we have S, P, D, and F. Each one of these orbitals can hold so many electrons. Okay, so I want you to write this down. The s orbital holds 2 electrons. That's the maximum number the s orbital can hold. The p orbital holds 6 electrons. The d orbital can hold 10 electrons. And the f orbital can hold up to 14 electrons. That's the maximum amount. Meaning your s orbital, you can have an orbital of 1s, 1, and that would tell you that we're dealing with hydrogen. And if that doesn't make sense, what I just said, don't worry. Right now we're just working on filling these boxes. So these boxes, each one of these boxes can hold 2 electrons. And those arrows are telling you the spin of the electron. So you'll see that some are pointed upwards and some are pointed downwards. That just indicates the positive and negative spin. So you have to fill, when you fill these boxes, so we're dealing with the p orbital in all of these. If you're looking at boron, I'm looking at carbon, nitrogen, and oxygen. They all are within that p orbital. Okay, don't worry about those superscripts right now. Just worry, and if you look up boron on the periodic table, it has 5 electrons. Okay, some of those electrons will go and fill in your s orbital first. Remember, s orbital holds 2 electrons. But for boron, it's special. It's not, I guess I shouldn't say it's special, but when we start filling these things in, we'll notice that there are 2 s orbitals within boron. And this will make a lot more sense when we start filling out our periodic table. I know, you're like, what is she saying? When we look at the p sublevel, there is only 1 electron present within that p sublevel. So for this example, I'm looking at just the p sublevel and that filling order. P sublevel has the possibility of holding 6 electrons. That's why there are 3 boxes here. Each box can hold 2 electrons up and down, like I had already mentioned before. So since boron, we're looking at this one here, 2p1. So we're in the second energy level, p orbital only. That 1 indicates there's 1 electron in that 1 orbital. So I would put just 1 arrow pointing up. You always point up first before you go down at all. Always go up before down. The second one, again, we're looking at carbon. We're looking at the 2p2, 2 electrons. So we go up and up. Nitrogen, 2p3, up, up, and up. Now we go to oxygen. It has 4 in that p orbital. So we're going to go up, 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 and then we add this one down here. So you always fill. This is Hunds Rule. You always fill with your, what I'm saying is that if you can have a box by itself, always be by itself. It's like these guys, these electrons want to be by themselves. They do not want to have a partner unless they are forced to do so. So that's the case here. I spent a long time talking about this, and I'm going to spend probably just as long or longer in class. So please, if you are still confused, don't freak out. I'm really going to try to make this as very, not easy. I'm not going to say easy, but hopefully a little bit more understanding. All right, so electron configuration notation. So what I mean by that is how do we write the exact placement of these different electrons? So in order to determine the notation, you must follow the 3 rules presented in the prior slides. So remember Pauli exclusion, Hunds rule, and Aufbau's principle. All right, so you need to use an orbital filling diagram to determine configuration. And once you get the hang of this, you actually don't need to do the diagrams as much, but it really will help you get an understanding of how those filling orders work. Again, another thing you need to determine is the number of electrons in a neutral atom. We are not dealing with ions right now. So just a neutral atom, what do these things look like? And perfect. I feared that this would happen, that the periodic table would not be on here. And I don't know why the picture did not show up, but it is okay. That just means your video is going to get cut short a little bit. When we are in class, we are going to go over where the orbitals are located, and hopefully this will help bring all of that information and really bring it whole circle. If you have any questions, please ask me on Edpuzzle.